Hi everyone, and thanks for the introduction. This work is done in the collaboration with the Ant group. And secure collaborative machine learning, I think we are referring to the same thing as the last speaker. He called it PPML, I call it SCML, but we are referring to the same thing. And it enables multiple parties to train a model or perform inference tasks with their private data, like the training set, model weights, and the user request. And it protects sensitive information by encrypting data with some secure protocol like secret sharing, oblivious transfer, and homomorphic encryption. And because the participants are separated, and there are encryption, so there will be a lot of ciphertext exchange and a large amount of communication time. Existing some optimization, they usually focus on how to improve the protocol efficiency. Instead, we propose interconnecting the parties with high-speed RDMA network. And RDMA has been widely deployed in today's machine learning clusters, so it's very reasonable to do this. Although we can set up the high bandwidth network, existing SCML, they fail to utilize the bandwidth because existing implementations still rely on the traditional slow TCP network. As we can see on the left side, the sending message is processed in the operating system kernel through a very complex transport layer mechanisms like the data copy, packet preparation, congestion control, which will consume a lot of CPU cycles and is bounded by the CPU performance. The maximum bandwidth of a TCP flow on the single core is usually less than 30 GB per second. In contrast, RDMA network can offload the network stack in the hardware, bypassing CPU processing and OS kernels during data transmission. It provides a distinct network interface that allows the sender directly write the message to the receiver side without interrupting the remote CPU and the OS kernel. So the existing commercial RDMA cards can reach up to 400 GB per second, and the bandwidth is still growing. By the way, we don't use RDMA in existing SCML, not because the developer don't know them. It's because unleashing RDMA performance is very hard in the SCML setting. Our primary challenge is the mixture of protocols. Suppose we have received RDMA message, and the messages are in a staging buffer. And SCML usually have multiple protocols and the encrypted data. The different protocol messages are mixed in the staging buffer. However, RDMA cannot notify the receiver side about the protocol efficiently. And because it bypasses receiver CPU and OS kernel, we don't know the message arrival, we don't know the message position, and we don't know which protocol should process the message. It seems we have to add extra headers on the message and implement gates, but it will bring extra copies, which is not desired if we want high bandwidth. To solve this problem, we combine RDMA protocol communication patterns. Instead of putting message in one single staging buffer, we dispatch protocol message on sender side by sending them to different destination address. Our key observation is that the protocol communication patterns is irrelevant to the input. This feature allows to pre-configure the destination address for a protocol to place their message, which enables to know the protocol based on the message addresses. The second challenge is the heterogeneous configuration of parties. Since the parties are different entities, they may have different runtime configuration, including the message size and sending order. This causes two situations that cannot be solved by RDMA directly. First, the receiver side may expect different lengths because of different message segmentation strategies. And second, the receiver side may expect different order of the sender side. Existing RDMA enabled like the communication framework, for example, like MPI and NICO, they are mostly designed for single user and the same configuration. We need to divide, merge, or reorder the message, which will lead to suboptimal performance. To solve this problem, we exploit the high-level structure of the machine learning task, especially the matrix shape. In a collaborative machine learning task, the parties will define the same model and same task and run the task collaboratively. They have the same matrix shape. So we can associate protocol message with the index of elements in the matrix that produce that message. With this element index, we can locate the protocol message no matter the order and batch size configuration. For example, given this 4-element matrix, we mark them with a position, and no matter the order of message, we put them according to the element index. So we can also pre-configure this mapping, and it can be done without runtime information. Finally, we consider the implementation effort for protocol developers. SCML is an active field with new protocols every year and new implementations. If adopting RDMA in every new protocol requires significant effort, and it will be difficult for protocol developers who are not RDMA experts. To solve this problem, we built abstractions of RDMA communication in the SCML setting. We've done this by using data parallel feature of machine learning task. With data parallelism in the training task, each data sample is processed with the same training function, producing the same pattern as other data samples. This is true for the potential secure protocol that iteratively applies to all data samples, and we can build a socket-like interface that automatically send receive with a pre-configured remote address. We had the detail. And we assembled the observation and built a system called CORA, which means collaboration over RDMA. It's a protocol-aware RDMA framework designed for the SCML. At its core, we built a data structure called protocol context to enable RDMA communicates with the knowledge of upper layer protocol. The CORA has 3 key capabilities. First, it automatically identifies the message and protocol without extra copies or adding message headers. Second, it allows communicating with different message lengths and message orders. And third is scalable to new protocol by automatically managing the protocol context. For a single protocol context, it's allocated with a buffer to store the protocol message and a unique ID. Each protocol context has a unique ID encoded as part of the intermediate data carried by the RDMA operation. We also encode the index of elements associated in the protocol to deal with out-of-order issue. On the receiver side, it gets arrived RDMA message and the intermediate data, decoding the protocol context, element index, and check the message length. The receiver knows the receiver address position by checking the protocol receive buffer and the element index, which is part of the encoding. And protocol contexts are managed automatically. The allocation release is managed based on the dependency of machine learning layers. For example, when performing collaborative training on this 3-layer model, we allocate new protocol context when the party is stepping into a new layer. The layer calculation dependency is like the layer 2 depends on layer 1 and on layer 0. When allocating protocol context on layer 2, we know that the layer 1 has finished on this side, but we don't know it's finished on the other side, so we cannot release them. But we know that the layer 0 must have finished because we cannot start layer 1 without layer 0. So we can release layer 0's protocol context, and in general, we can release layer k-2 when allocating the layer k. For existing protocol implementation, we can integrate CORA by replacing the TCP communication. CORA is designed with a very socket-like protocol API to set up RDMA connection with party ID and number of parties, the memory pool for the message receiving. And for every layer and protocol, we create protocol contacts with requested message buffer size and array length. To replace TCP, we use a pointer of the buffer of the protocol context, and you can fill the protocol. You can fill the buffer with send message with the pointer and send data with the API directly. For receiving data, you can also use receiving the next buffer and receive with locating the element in any position. To show the speed up of CORA, we integrate CORA into a GPU-based collaborative machine learning framework. It's called Piranha. It's work published in 2022. Our testbed has 4 nodes and 8 GPUs. The network speed is set at 100 GP per second. The baselines are TCP and RSocket. TCP is the baseline basic default communication, and RSocket is a general purpose RDMA communication framework. It's similar to kernel socket. It uses a ring buffer to stage the sending message and receive message, which will introduce extra data copy and might lead into suboptimal performance. We replace the kernel socket and kernel socket send and receive with RSocket to implement that baseline. Before running the end-to-end training type, we first evaluate some performance of the basic operations, like the oblivious transfer protocol, triple generation, and the matrix multiplication under 2, 3, 4 parties in the semi-honest setting. We can see that the green line CORA causes less time, the least time compared to TCP and RSocket. And for the training and inference tasks, we set 2, 3, 4 parties under semi-honest assumption and recorded online cost. And again, CORA is faster than TCP and RSocket on all test cases. So if you are interested, you can access the GitHub repo and implement your new protocol and enjoy the performance. If you have a problem implementing, you can drop me an email. Thanks, everyone.